over the total time. And this is what you guys all intuitively did. You took the total distance traveled, 220 miles per hour, and you divided by the total time which you left. Alright, cool. Now, let's make a graph, because graphs are fun. So, here's a graph. What I'm going to make a graph of is the distance versus time. So, and over here, we'll put sort of like DC at the bottom, and we'll put New York at the top. So let's say this is the 240 mile mark. In other words, like that means I'm in New York. And we said that it took 4 hours, right? So this is time like in hours. And now let's suppose, Rohan, let's suppose that thing, which I just said a minute ago was absurd, that we were going 60 miles per hour literally every second of the entire trip. And let's suppose that was actually true. So what is the graph? What is the distance versus time graph going to look like if I'm going 60 miles per hour every second of the entire trip?
A line.
Just a line, just a straight line. Alright, so this is just like common sense, or you have some experience with physics and distance versus time graphs, or just duh. Yeah, I'm gonna have this is gonna be a straight line. So this is like, Rohan, this is like you like revved your engine, and you just like were already like you just dropped out of your bat cave and like already like hit the ground. You were already going like 60 miles per hour.
Moving train.
Yeah, you drive off a moving train, something like that. Yeah, good one. All right. So anyway, this is the picture. It kind of looks like this. All right, just to make sure you have this average speed conversation under control, I'll just ask a whole bunch of questions now. So, I guess this first question is kind of boring because we already answered it. But what is the average? So, what is the average speed? Or actually, let's do this. What is the average speed on the interval 0-2? Total distance traveled. What was the total distance traveled? Eric, how much distance did I travel over the first 2 hours? 120 miles. And how long elapsed? If I mean, 2 hours. So you are exactly right. The average speed on the interval 0-2 is 60 miles per hour. How about the entire trip, right? What is the average speed on the interval 0-4? Eric, again, what was the total distance traveled on the interval 0-4? 240. And then how many hours left? 4 hours. Okay, so again, we have 60 miles per hour. Okay, so this example is kind of boring. Your speed is just constant. Speed's constant the whole time. And any interval I choose is going to have the same answer. Okay, let's make now a less ridiculous graph of a trip to New York City. So let's make this a little bit more reasonable. And now we will still travel 240 miles. We will still achieve the trip in 4 hours. But now we'll start going zero like a normal. This is what my normal trip to New York City looks like.
That's a lie. That's a lie. Yeah, there's like all this like.
Oh no, they got those new tolls that just take a picture and stuff now.
There's that bridge that's always really backed up.
Oh yeah,
Whoa.
that big bridge.
Aw, you guys have like lived experiences in your life. So cute. Okay, so this is a graph. This is a graph, and this is the distance traveled, and this is the time that's left. Can someone explain, like in words, like about this particular trip, to this particular joyride to New York City? Shivani, explain in words. What's going on here?
So you're going slow.
Yeah, pretty slow.
In the beginning.
Yeah.
And getting faster.
Yeah.
And then slow.
Wait, and then slow? When did the slow happen?
When it's a bridge.
Oh, then you just stop, right? Yeah. In fact, as Lathrop said yesterday, you ram into New York City at 400 miles per hour. That's how he phrased it.
How would you pass all the traffic?
That's pretty much, this is pretty much how it's going. So, okay, this is exciting. So now I can ask a whole bunch of questions. Like, what is the average speed on the interval 0-2?
30 miles.
Someone who hasn't talked yet. Megna. Oh, man. Jesus. Megna, anyway. What's the total distance traveled? I know. I'm sorry. You said I love you.
60 miles.
Yes, that is correct. Based on looking at the graph, we see that we have traveled 60 miles. And how much time elapsed?
2 hours.
2 hours. So what was our average speed over that time interval?
30 miles per hour.
30 miles per hour. That's pretty terrible. That's pretty terrible rates on intercity traffic. Okay, but Magna, the story gets better. What is the average speed on the interval 2-4? How much?
90 miles per hour.
Yeah, explain. How much distance did I cover on the second half of the trip?
180 miles.
Yeah, 180 miles.
What happened
And then
when you
how long did that take?
Miles per hour.
2 hours. Yeah, so that's pretty good, right? The second half of the trip really made some good time. 90 miles per hour. So all of this is very exciting. All right, so a couple things I'm trying to get your brains on to be thinking about this kind of stuff, and also I want to just stress the fact that average speed, Raymond, average speed, this is a pre-calculus concept. This does not require any advanced anything, right? Anyone can do this. Anyone in middle school understands what these things mean. All right, now we're taking it up a notch. Matteo, I give you this graph. And now I want to ask kind of a weird question. Enough of this average speed stuff. I would like to know, at precisely the 3-hour mark, at exactly time t equals 3, how fast am I going?
Is it like a tangent?
Yeah, well, called them the wrong person. How fast am I going? All right, so what I want to know right now, what I want is I want my instantaneous speed at t equals 3. How fast am I going at that exact moment? Seems like a reasonable question. Talk to me about this. Except not Matteo. Did I spell it right? Yeah. Instantaneous speed. What does that even mean?
Yeah.
What does that mean?
Yeah. Just say at that.
Anyone, I just say some things, yeah. Whatever, Emma.
You could travel back in time and look at the speedometer.
Travel back in time. Okay, yeah. In fact, what if the moment were just happening? What if you were just you were sitting in the passenger seat with your stopwatch and you're like, Mom, how fast are you going now? What would your mom do?
Look at the thing.
Shut up.
Look,
Yeah.
shut up, I'm trying to drive.
That's actually.
Or,
Stop distracting me.
or we're just probably just look at the speedometer or whatever, right? Okay. So
Okay.
So that's one answer. Right. Rohan, this is a weird question because here's how I feel about this a little bit. We talk all the time about how fast you're going, right? You're I'm going this fast at this moment, right? So this seems completely normal. Yet on the one hand, when you start to think about it, can I get a definition? Rohan, give me a definition of instantaneous speed. What does that mean?
The speed at a particular moment in time.
Yeah, okay, the speed at a particular moment. All right, but it's getting kind of weird, right? You're making a face. Does that mean you're thinking? It's not weird, it's just a weird face. Penny, is that a hand?
No.
Robbie Fleischman.
It's kind of weird because speed is distance over time. If you're instantaneous, there's not really a time as doing distance over. It's kind of a weird term.
So what?
Yeah, Robbie Fleischman. Say it one more time. This time, for real, louder.
It's kind of a really weird term because speed is just your distance over your time. And if there's no time because it's instantaneous, then you can't really say what the instantaneous speed is by measuring it. You have
So why
to
you asking us
use
this
other
question?
methods.
I don't know. Yeah, that's exactly correct, right? The general way that we understand speed is that it's distance over time. It's the distance traveled over the time that elapsed. But if I'm asking for how fast I'm going in a particular moment, Stephen, how much distance have I traveled at a particular moment?
0.
0. How much time has elapsed at a particular moment?
Doesn't matter. It's still be
0. So actually, I have no idea what the hell is going on now, right? Suddenly this concept, which I thought seemed pretty clear to me, now is anything but clear. I don't even know what instantaneous speed means anymore. What's distance over time at a moment? That doesn't even make any sense. lots of infinity going on here, as you can see. Now we're talking about sort of the infinitely small, and it's hard to even understand like it's hard to even understand like what's going on. I'm not even sure that this concept is coherent. It's something that makes sense when you don't think about it too much, but then when you start to think about it, it starts to make less and less sense. All right, Ethan, we need to solve this problem. Maybe not today though. Maybe today. Maybe right now. Ethan. What okay, so besides looking at your spot, like what's another time that we often talk about like how fast you're going at a particular moment? You guys like driving yet? Who drives? Who's like a driver's license? Do you have a license?
No, permit.
Permit?
I'm gonna get mine soon.
Okay. Sometimes even when you're just pretty much minding your own business and driving safely, if you exceed certain arbitrary limits that the man has set up in advance to trap you, then you'll get in trouble. And you'll get in trouble and you'll be declared to have like broken laws. And what they will claim is that you laws, exactly. And they will claim that you have gone over the speed limit. And what they mean is that at a particular moment, you were going like too fast, right? That's kind of what they mean.
Yeah.
Right. You can't just tell the police, well, I was stuck at a light, so my average speed over the last 5 minutes was like not that fast at all. Okay, that's not what they mean, right? Implicit in the very concept of speed limit is that at no moment can you be going faster than speed. Okay, so how did they catch you? Yeah. Like shout some stuff out.
The little, what's that thing called? The
speed gun. Speed gun. I don't know what it's called either. Okay. So, yeah, there's like a radar gun, right? Okay, so there's a radar gun, and there's a speed gun and blah blah blah. All right. So again, I have to apologize to the internet. I'm going to stop doing this. I don't actually know how radar guns work, and I don't want to know. Okay. One year I looked it up, and it was like way more complicated than I would have thought it would have been, or something like that. So. We're going to do is we're going to pretend that radar guns work this way, and never mind that this is not actually correct. Okay, so this is better anyway. All right, so let's imagine that you're a radar gun. And radar guns like shoot out radar pellets or something, and then the radar. We don't need to know physics. It's it's too hard. We're going to shoot out radar, whatever that means. We're going to shoot out a radar pellet, and then it's going to come back, right? That's kind of how the gun works. So we need to think that we need to get our head around this concept. So what's going on? What does that do? So what? Yell.
So if you have 2 radar pellets, sorry?
Yeah. You just went right to the end. Let's start with 1 radar pellet. But yeah, you are correct. What can I do with 1 radar pellet?
You just bounce it off.
Far away.
You bounce it. Okay, but explain how that works.
So it bounces off.
Uh-huh.
And then comes
back. Yeah? We're just making stuff up, so you can't be wrong.
And you say, okay, I sent this at 2 o'clock exactly.
Yeah.
And it came back at this time, and I know it travels at this speed, so the car is that far away at that moment in time.
Exactly. Pause for a second. It's not that hard. I think everyone needs to get their head around it. Yeah, you have a radar. The radar pellet moves at some particular fixed speed that we know about, like for sure, and doesn't change, like something physics, blah blah blah. So you're holding the gun. You point the gun at some object. The radar pellet goes out, and you know precisely the speed of the radar. So it goes out, it bounces off the object, it comes back to you. So your gun is sensitive enough that it's measuring the exact amount of time that's elapsed in between when you shot it and when you received it back again, and you know the speed at which the thing travels. So using 7th grade math, we can know precisely one thing at this point. Everybody? Where the car was at the moment that the pellet hit the car. That's all we know, right?
Yeah,
we know the distance. We know the distance from the gun to the car at the moment that the pellet hit the car. Okay, so that's not enough. But what Yael says is, okay, we don't just send 1 pellet. We send 2 pellets. So if we send 2 pellets at some fixed time gap apart from each other, right? Then the 2 pellets, boof, and they go out. They both hit the car. They both come back. And the gun measures not just the time that elapsed between the first pellet hitting the car and coming back, but also the second one, right? So now we know where the car was at a particular moment, and then where the car was like half a second later. And then
we know the speed.
We know the speed. Sort of. Someone elaborate on that a little bit. What do we actually know? Yeah, Raymond.
The average speed on that time interval.
Yes, what we've actually calculated with just 2 points, and you with me? What we actually calculated is the average speed over a very, very small time interval. Okay, so in some logical sense, perhaps that's all we can ever do. All right, so let's make a picture of this. Now we're just getting a little bit serious. You gonna move? What's up?
Wait, but if you're actually bouncing off pellets, wouldn't they come back faster because the speed of the car, like, with the selection?
Yeah, you have to control for things like, let's assume the gun is not moving. Yeah, but it's like electromagnetic radiation is moving at like a fixed speed and stuff, right? Isn't that the idea? Yeah. Pellets was like a, I'm just speaking quantumly, so I'm going over to the next level. All right. Okay. So now we kind of get serious about our task here. So let's suppose I'm going to make a distance versus time graph. Distance versus time graph, and we're going to do this like in general. So let's suppose that my picture looks something like this. Also, can you raise the backboard or somebody? So let's suppose that my distance versus time curve looks something like this. And the goal is find the, and now what I want is instantaneous speed at time t equals c. I'd like to know how fast the car is going at exactly time c. And actually, I can give this function a name. I can call this function like f or whatever, and that means I have a point on this graph, c comma f of c, and of course this is distance, so that means like f of c represents like how far away the object is at time c or whatever. All right, I want the instantaneous speed at time t equals c. Okay. Well, as we've been discussing, that's like sort of impossible or whatever, right? So what can we do? What can we do instead? Alice, what do we do?
Find the average speed over a small interval.
Find the average speed over a very small interval, she says. Yeah, and that's what we can do. So what we will do now is we will pick another point, not that far away, very, very close to C, picture not to scale. Pick a point D.
What?
I said, pick a point D, which is very, very close to C, picture not to scale.
Oh, picture.
And this is the point D comma f of D. All right, and now, instead of calculating the instantaneous speed at time c, we will instead calculate the average speed on the interval CD. Okay, and then this is something that we just know how to do, right? What is the total distance traveled on this interval? Yeah, f of d minus f of c. And what is the total time that has elapsed? D minus c. All right. Does this look familiar to you at all? This thing? It's like rise over run. Yeah, this is supposed to remind you of slope or whatever. And in fact, one of the reasons why they spend endless months in Algebra 1 going on and on about slope is because it is sort of like a concept which is very important to have in your understanding to understand these more advanced kind of concepts. And if you see, well, what is the numerator here? The total distance traveled. Well, that's just the difference in the y-coordinate at time d versus the y-coordinate at time c. So this is f of d minus f of c. And then the time elapsed is d minus c. So this is like rise over run, but it's like rise over run for what? It's rise over run, but usually that's talking about lines and stuff, right? Yeah. Yeah. So what line is this the rise over run for?
That line.
That line. Okay, I'll take that answer. Yeah, that line. The line through points C and D, right? Is everybody with me? All right, so Sandeep, this is like easy and yet sort of like deep and important, right? This is the line which goes through the points C, comma f of C and D, comma f of D. There's a name for this line. It is called a secant line. And this line sort of cuts the function in two different places. That's why it gets that name. And fundamental understanding, which does not require any calculus or anything, is that the average speed of a function on a time interval is just, if you have a distance versus time graph, the slope of the line through those 2 points. You agree? Okay. All right, so, however, that's not actually what I wanted. What I actually wanted was the instantaneous speed at time t equals c. So what do I do?
Yeah.
Does everyone feel this? This is like, it's like in the air, right? Yeah, what we need to do is we need to move these points, like infinitely close together, whatever that means. And what happens when I move these 2 points infinitely close together? What happens if I move point D infinitely close to point C? Just closer and closer and closer and closer. It becomes the tangent line. And this is what Matteo said like 15 minutes ago. Because he just like knew or something.
Yes.
That if you move the 2 points, if you move point D infinitely close to point C, whatever that means, then what you end up with is a line which is tangent to the curve. Just like a tangent line to a circle touches the circle at just 1 point, the tangent line to a function touches the function at just 1 point. And so the big idea here is that when one wants the instantaneous speed of a distance versus time curve at a particular point, what they really want, therefore, is the slope of the tangent line, right? If I can somehow figure out the slope of the tangent line to this curve, then that represents the sort of average speed at a sort of infinitely small time interval. You with me? Okay, so this is the tangent line problem. This is half of calculus. Half of calculus is solving the tangent line problem. What is the tangent line problem? The tangent line problem is find the slope of the tangent line to a curve. And while I can just phrase that as like a math problem or like a geometry problem or whatever, I think it's important to understand the whole point of the problem. The point of the tangent line problem is that it gives me instantaneous speed. Okay, so goal, Ethan, goal. Given any arbitrary function whatsoever, and given any arbitrary point whatsoever, what we seek is some method for determining the slope of the tangent line to the curve. Everyone get it? Okay. While I have you all physicsy, let's return to the area problem.
Oh my gosh, I just literally
Okay, so now the first time we looked at the area problem, we were pretty much in like the time of ancient Greece. Now we fast forwarded over there on the other board with the tangent line problem to like the time of Newton, like 400 years ago. So now area problem revisited. Area problem revisited. A new trip. Suppose I'm going at 60 miles per hour and I travel for 4 hours. Yeah, how much distance did I travel? This is like easy, right? 240 miles. You don't need to know any advanced math for this. You just like, if you understand what miles per hour means, then you just like, have the answer already. Okay, we can make a graph of this, however. It's quite boring graph. This is different from the graphs we've made previously because now, instead of graphing distance versus time, we're going to graph speed versus time. So I have the speed over here and I have the time over here. And traveling for 4 hours. This is a quite boring graph because the speed is constant, right? It's just 60. So if the speed is 60, what does this look like, Calvin? What's that? This, yeah, that one. Flat line. Okay. How did you get? Okay, so I guess what's going on here? How'd you get 200? How'd you get 240? Uses?
You multiply the two numbers together.
We just multiply the two numbers together. And uses like there's like some like deep kind of like sort of conceptual model of what multiplication means. What is that?
Rectangles.
Rectangles. Yeah, Emma, is that what you're gonna say?
Yeah.
Yeah, that's right. In fact, there is kind of like a rectangle here, and you can see that like this rectangle. Well, this dimension of the rectangle is 60. This dimension of the rectangle is 4. And in fact, what we just do on some level when we multiply these two numbers is we just take the area of the rectangle whose side lengths are 60 and 4. And indeed, what we get is 240. And even the units work out, right? I mean, this is like miles per hour, and this is hours, and when you multiply them, you get miles. So that's beautiful. Okay, beautiful yet sort of like maybe a little bit boring. A new problem. Now, I am going to proceed.
Oh, I see.
I'm going to take a trip, but the trip is going to the speed at which I'm going is going to be like a step function. So for the first hour, I'm going to go 30 miles per hour, and then here I'll just draw it. This is pretty fun.
Wait, what? You just all of a sudden jumped to.
Yeah, this is kind of a crazy trip, right?
What?
Sydney, explain what happens.
I mean, you start driving and
You get
then.
hit by a train.
Yeah.
This is really, ooh, that's a good. Ooh, this is gonna be fun. Yeah.
You start,
Yeah. This
like,
is
first off,
this
you
is a
start
really.
out at 30.
First of all, you say you spend the entire first hour going 30 miles per hour. Oh, I started. Yeah, you spend the entire first hour going 30 miles per hour, and then instantly at time 1, you shift into like some kind of weird hyper gear, or you get hit by a train, and you instantly get hit by. That actually makes total sense.
From
behind,
behind.
like the train's going 60 miles an hour from behind, and it
Wait,
just
why are
hits
you driving on the train track?
There's a lot of things that we don't understand about this.
So you can go faster. When the train-
But yeah, we instantly start going 60 miles per hour, and we keep up that speed for 2 hours, and then in the 4th hour we're going 90, right?
Train gets high.
Okay, so how much total distance did we travel in this trip? Well, how much distance did we cover in the first hour? Kendall, how much distance did we cover in the first hour? 30 miles. How much distance did we cover in the middle 2 hours?
120.
Yeah, 120 because like, duh, right? Now I went 60 miles per hour for 2 hours, so by multiplying those two numbers together, I get, or by taking the area of the rectangle, which amounts to the same thing,
I've seen
then,
this before.
really? Cool. That means we're going 120 miles. I guess you probably did this in freshman physics, maybe?
Yeah.
Yeah. And then in that 4th hour, I was going 90 miles per hour times 1 hour, so I covered a distance of 90 miles. And when you add that all up, you get like 240, right? Okay. So here's what's going on here. What's going on here is I begin to associate the area under a speed versus time curve with the total distance traveled. There seems to be some kind of association here. Now, things get complicated. This is our last graph. And can someone erase the backboard? That'd be nice. In this last graph, I have a variable speed. So now I still put speed over here on the y-axis, I still put time over here, but now we're kind of just going to go like, something like this. So maybe that's 4, 2, 3, 1. Okay, so supposing that was my speed, now what I would like to know, given this very particular speed versus time curve, is how much distance did I travel? How much distance did I travel? Well, I don't really know how to do this. So what we have to do is, Kevin, what should we do?
Oh, you could kind of split it up like you did with the second graph into infinitely small bars until there's essentially a bunch of rectangles next to each other, then kind of add them up, but you can't really do that.
You're pretty much exactly right. Internet, did you hear that? I think you heard that. Calvin, everything you said is exactly right. You split up into a bunch of little rectangles. In fact, that's what we're going to do right now. We're going to just go, but we're not going to go straight for infinity because that's hard to draw. So we'll just go for like 1, right? So at time 1, you can look at your speedometer and you can be like, yo, this is how fast I was going. And then what we can do is we can pretend that we were going that fast over that entire first hour, even though that's not true. So I'll take the area of this rectangle. The area of that rectangle represents how much distance I would have traveled if I were going for the entire hour at the rate I was going at the end of that hour. Follow? That was a big sentence. Okay, now at time 2, I can check my speedometer again. And I can pretend, overestimating pretty heavily here, I can pretend that over that entire second hour, I was going at the rate that I was going at the end of the second hour. In which case, the area of this second rectangle that I've drawn represents the total distance traveled, if that were true. Eric, you got this? Okay, again, now I go up to 3, and now I pretend, I draw another rectangle. This represents the total distance traveled if I had been going that speed the entire hour. And finally, over here at 4, I draw a rectangle. This one kind of underestimates. This represents how fast how much distance I would have traveled over that interval if I had been going at the rate that I was going at the end. If I add up the areas of all 4 of these rectangles, I will get a kind of ish, sort of decent approximation of the actual distance traveled. If I want to know the actual distance traveled, then what I need to do, well, what do I do?
An infinite amount of...
Split it up into smaller intervals. And in fact, Calvin just went right for the answer. He said, what I actually need to do is somehow, whatever this means, split it up into an infinite number of intervals. So that sounds like calculus, right? Because it's like infinity. So yes, this is the true modern area problem. The modern version, and when I say modern I mean 400 years ago, version of the area, modern as opposed to ancient, the modern area problem is the problem of, given any function whatsoever, an arbitrary function, and given some particular time interval, figure out precisely what the area under that curve is. Because the area under that curve will give me, I feel, the total distance traveled. Okay, Mateo, are you pumped?
Yeah.
Those are the 2 problems of calculus, and I promise you that we will have them solved by like May. All right, this took, that was your introduction to calculus. Sydney, you feeling pumped? Are you clapping? Aww. Oh, should we do a 1 minute? I planned to do this before, but then I just forgot. We should just introduce everybody in the class. If you're actually watching these videos, I'm so impressed. I'd love to know who you are. Email me if you're on YouTube or something.